Oops, I was muted. What I was trying to say just now was, in the third part of this video, I'd like to tell you about our third and final pair of graph transformations, which are the stretches and shrinks. Oh, I would have been real mad at myself if I had stayed muted for the whole next 30 minutes. So once we have these, we'll have every transformation we need to, for example, start with the toolkit parabola and make any other parabola. We'll have enough to do that. So this is that final step. Stretches and shrinks. So imagine I have, say, the absolute value function. And I would like it to be pointier. Imagine I draw it on a sheet of rubber. So this whole graph is rubber, or like a water balloon. And then you blow up the balloon. So the whole rubber, all the rubber stretches. We get something that stretches out vertically, like so. It could end up looking maybe like this. So every point, let's say we stretch it 2 times, where it was a foot long before, now it's 2 feet long. So maybe this is the point 2, 2, and this is the point -3, 3. If that's stretching out to double its previous length, then this distance is going to be 4. So this is going to be the point 2, 4. And this will be the point -3, 6. So it's stretched. Every point is twice as far away from the x-axis as it was before. If there are points down here, they would stretch to twice as far away as well. The way we're going to do that is this new curve is going to be y equals 2 times the absolute value of x. So we're going to change f of x into some number times f of x, and that's going to give us a vertical stretch. If I wanted to shrink it instead, let's say I wanted to make it 1/3 as tall, I could draw the graph y equals 1/3 absolute value of x. And there, instead of having 2, 2, you'd have 2, 2/3. And over here, you'd have -3, 1. So this graph has been flattened. So that's a vertical stretch or shrink. You multiply your output by a number, and all the y coordinates get magnified by a factor of that number. So again, this is a vertical transformation. It's only going to affect the y coordinate, not the x coordinate. So this is a vertical stretch. Now, what if I want to do a horizontal stretch? Then I'd have to multiply the x coordinate, right? So let's say I change, let's say I have f of x equals, I don't know, how about the square root of x? And let's say I turn that into g of x is f of 2x. So that'd be the square root of 2x. I've multiplied the input by 2. Think back to horizontal shifts. What would you expect this to do? So we have points like 4, 2 and 16, 4. This is the square root of x. This is f of x. So if I make g of x, let's try this. What would g of 8 be? It's the same as f of 2 times 8, which is f of 16. So g of 8 is the square root of 16, which is 4. F, when you plug in 16, it gets you a 4. So g, when you plug in an 8, gets you 4. This multiply by 2 in here, we're multiplying our input by 2 before f sees it. So it's like a 50% off discount on our inputs. Our money goes twice as far. We only have to pay 8 for a 4 instead of paying 16. So here's the point 8, 4. That's going to be on g. And if I take g of 2, that's the same as f of 4, which is 2. So I'll have the point 2 right here. So each of these points has regressed halfway back to the y-axis. And so this whole thing is fatter and skinnier. Or sorry, that doesn't make any sense. It's squished to be skinnier. That's what I meant to say. So when you multiply, you shrink. So how would I stretch? And you probably guessed it. If I say h of x is f of 1/2 of x, then my money's only going to go half as far. So I know f of 16 is 4. So if I want to get a 4 out of h, I'm going to have to pay twice as much. H of 32 is the same as f of 1/2 of 32. So that's f of 16, which is, so h has the point 32, comma 4, and h of 8 is f of 4, which is 2. So now our money only goes half as far as it did with f. So here's the point. Eight, comma 2. So h is stretched out. It's longer and fatter than f is. For another example, if this is the graph y equals x squared, then this is the graph of y equals 2 times x all squared. Why did I put parentheses there? If the 2 was outside the parentheses, it would be a vertical stretch times 2. If it's inside the parentheses, it's a horizontal shrink times 2. So this big fat parabola here, maybe this is y equals 1/3 of x all squared. So that's a horizontal stretch times 3. This is a shrink times 1/2. So if I change f of x into f of a times x, it's a stretch by 1 over a. So there you go. That's our 6 graph transformations. Let me put a table here so we can look these up quickly. So we've got a horizontal shift, and that's where we make f of x minus a. We've got a vertical shift, and that's where we make f of x, and then we add b on the outside. We've got a horizontal stretch, and that's where we do f of 1 over a times x. We've got a vertical stretch, that'll stretch by a factor of a. So if I did f of 1/2 x, I'd stretch by 2. Vertical stretch, I would do f of x and then multiply the whole thing by b. Horizontal flip, that's f of negative x. Vertical flip, that's negative f of x. So those are our 6 graph transformations. That's all 6 of them. Shifts, stretches, and flips. Some patterns. The shifts are based on addition and subtraction. The stretches are based on multiplication and division. And the flips are just a minus sign. So that's one pattern. Here's the other pattern. The horizontals are inside the function. So this minus is inside, this division is inside, this minus sign is inside. And they're also kind of backwards. We have to divide to stretch, and we have to subtract to go right. Whereas the verticals are, whoops, that's not spelled right. The verticals are outside, and they're normal. So this is adding on the outside to shift, multiplying on the outside to stretch, negating on the outside to do a vertical flip. And remember, a horizontal flip, that's the same as a mirror on the wall because it flips side to side. A vertical flip is the same as a puddle on the ground because it flips up and down. So when you do these transformations, the 3 horizontal transformations, they will only ever change an x coordinate. The 3 vertical transformations, they'll only ever change a y coordinate. we're ready to start putting all of the transformations together almost. There's one problem that we have to tackle as we begin doing this. What if I say, I want to know what order I'm supposed to apply these things in. So let's say I have a vertical shift and a vertical stretch. What's an example of a function like that? How about y equals 3x squared plus 4? This times 3, it's on the outside. It's not getting squared, so this is a vertical stretch times 3. And then this plus 4, that's a vertical shift, 4 units up. So do I do the shift first, or do I do the stretch first? Or does it matter? Let me try it each way and see what we can find. If you're not sure how a math concept works, you can always play with it until you decide how. Experimentation is a fine way to try to understand these things. I encourage it. So let's shift first. So here's y equals x squared, and it's got the point 1, 1. I'm going to keep track of this point. If I shift first, then it's going to go 4 units up. So it's going to move up to 1, 5. The y coordinate went up by 4. And then we're going to multiply that coordinate by 3. So we're going to do a stretch, and this is going to be a very tall, skinny parabola way up here. And this is going to be the point 1, 15. But if we stretch first, we'd start with this point 1, 1. The stretch is going to multiply everything by 3. All the y coordinates, that is, not the x coordinates. Those stay the same. So this becomes the point 1, 3. And then when we do our shift, this whole thing is going to move 4 units up, and this is going to be the point 1, 7. So you see we get a different answer depending on whether we shift first or whether we stretch first. So the question is, which one is correct? How can I decide which one of these graphs actually represents the function? Well, the x coordinates are both 1. So if I plug one in and see what the output is, then I'll know. So I know that f of x equals 3x squared plus 4. So f of 1 is either going to be 15 or it's going to be 7. Let's see which output we actually get. 3 times 1 squared plus 4. Well, that's just 3 plus 4. That is 7. So this graph is correct, and this graph is wrong. So it turns out we have to do the vertical stretch before we do the vertical shift. Now we could do the same thing with horizontal shifts and see what happens there. In fact, we could compare all of our transformations to each other and see what order they have to come in. You've seen how to set up one of these experiments, so you can conduct that experiment yourself anytime. What I'll tell you is the order, oops, I'll save you the time. The transformations go in this order. One moment. Excuse me, okay. If there is a horizontal stretch, it must be the very first thing you do. And if, damn it. If there's a horizontal shift, it must be the first thing you do. And if there's a vertical shift, like the one we had up here, the vertical shift must be the last thing you do. All the other transformations, the stretches and shrinks and flips, those can go in any order. As long as the horizontal shift is first and the vertical shift is last, you're going to be just fine. So let's practice some graph transformations. Now we're ready to so I'll give us some functions, like say f of x equals negative 1/2 x minus 2 squared plus 3. And the way we want to graph this is we want to identify what the transformations are. We want to figure out what order to put them in. And then we want to, after we know what order we want to put them in, geez, I'm having trouble talking today, aren't I? We want to identify the transformations, decide what order to put them in, and then apply them one at a time. And I'm going to keep track of a couple of points so that just like I did up here, I'm going to keep track of a couple of points so we can check our work after. Okay. So what are the transform? You know what's making me feel so awkward with this lecture is I'm used to this being a very int thing. It's weird doing graph transformations alone. Hey, email me anytime. Tell me if you need more help with this. Bring a friend. It's better with more people. And we can do some of these examples in office hours. Oh, I really am moonbrain today. Okay. So what are our transformations? The horizontal shift, if there is one, has to be first. In this case, it's right here. This is a horizontal shift. It's 2 units. And which direction does it go? That's right, it goes to the right. A minus goes to the right, a plus goes to the left. Horizontal shifts are backwards, remember? What's another transformation here? We can identify this +3 pretty quickly. Now remember, that's got to go the very last, so I'm going to save that. That's a vertical shift. So how about this 1/2 here? We could do that next. That'll be, it's on the outside, so it's vertical, and it's multiplying or dividing, so it's a stretch. That's a vertical stretch. Well, really, it's a shrink because it's times 1/2. So that's going to make everything half as tall. How about this minus sign right here? It's just a minus sign. It's on the outside. So since it's a minus sign, it's a flip. And since it's on the outside, it must be vertical. We don't have to write anything for that. And now, like I said, this +3 has to be last because that's a vertical shift. And it's 3 up. Verticals are normal. Let's keep track of the points. How about 0, 0, and 2, 4 as we go through these transformations? So first I want to do a horizontal shift 2 units to the right. That means the whole graph is going to move to the right 2 units, and specifically each of our points will. So each of our x coordinates we have to add 2 to. So this, instead of 0, 0, we get 2, 0. Instead of 2, 4, we get 4, 4. Now we'll do a vertical stretch times 1/2. Everything's going to get half as tall. So this is going to get fatter and flatter. Whoops, drew that in the wrong place now, didn't I? It should be starting at the vertex here, 2, 0, fatter and flatter. God damn it. Okay, that doesn't look like any. I'll exaggerate. There, happy, happy, good parabola. Yes, that's ugly as sin, but I'm not redrawing it a 5th time. So the x coordinates are going to stay. They're going to stay 2 and 4. Half of the y coordinate 4 is 2. Half of the y coordinate 0 is still 0. This point hasn't moved. Now I need to do a vertical flip. So that's where we put the mirror in the puddle, and the whole thing is going to go upside down. So after this vertical flip, the graph is going to like fatter and flatter like this. So now this is the point 4, -2. All the y coordinates have been multiplied by -1. So what point is this? Well, it's still 2, 0. -0 is 0. Finally, I have to do a vertical shift 3 units upwards. So each of these points is going to move up 3 units, and so is the whole graph. So instead of 2, 0, we'll have 2, 3. Instead of 4, -2, we'll have 4, 1, because -2 plus 3 is 1. And then we can check our work. So I'd want to check, is f of 2 really equal to 3? Let's find out. F of 2 is -1/2 of 2 minus 2 squared plus 3. So that's 0 plus 3, which really is 3. So yeah, f of 2 really is 3. So that point's in the right place. And then if I want to be double sure, I can check f of 4. Well, that's -1/2 of 4 minus 2 squared plus 3. So that's -1/2 of 2 squared. So that's -1/2 of 4 plus 3, which is -2 plus 3 is 1. So f of 4 really is 1. So both of these points are in the right place. This is probably the right graph. There's the whole thing on screen one more time. You can pause it here if you want to look things over. Otherwise, next example. G of x equals -√(-x plus 2. What are my components? If there's a horizontal shift, it's got to go first. So I'm going to take a look at this plus 2. That's clearly on the inside, so it's horizontal. And it's addition or subtraction, so it's a shift. It's clearly 2 units. And you're right, that goes left because it's addition, and horizontals are weird and backwards. So that's going to go 2 units left to kick us off. Other than that, we've just got minus signs. This guy right here is a horizontal flip because it's on the inside. This guy right here is a vertical flip because it's on the outside. It doesn't matter whether I do the first one or the second. Let me rephrase that. It doesn't matter which one of these I do first. It works the same in either order. Excuse me. So I will draw a graph of my toolkit function. The only thing here that isn't a transformation is that square root sign. So I'm going to start by drawing y equals root x, and I'll pick a couple of points to keep track of. Let's just do something simple. How about 0, 0 and 1, 1? Easy points to keep track of. And now I need to do a shift 2 units to the left. How's that going to look? Everything will move to the left. So 0, 0 is now -2, 0, and 1, 1 is now -1, 1, because 1 minus 2 is -1. The next two are pretty easy. I need to do a horizontal flip. So we're going to put a mirror right here, right there, and everything's going to be flipped over that mirror. So this part is going to be on the right, and this part is going to be on the left. The new graph will look like this. So the whole thing, it's like we took a transparent piece of paper and flipped it over. That's how the backside looks. So now instead of -2, 0, that we have +2, 0, and instead of -1, 1, we have +1, 1. They've both flipped over the x-axis. And finally, we need to do a vertical flip. So now we're going to look at our reflection in this puddle here. So now instead, it looks like it's been reflected upside down. And so 1, 1 becomes 1, -1. Now 2, 0 is a special case. It stays 2, well, -0 is 0. And so that should be our final graph. Notice, since we did 2 flips in a row, this graph is actually the same as if we took this one, put an axle right here, and rotated it upside down. You see how this and this are just upside down versions of each other? So that's another way we could have done that, but I like to do them separately just to keep it simple. Let's go ahead and check our work. I had the points 2, 0, and 1, -1. So I'm going to check. g of 2 is the negative root negative 2 plus 2. So that's negative root 0. Okay, that really is 0. And how about g of 1? That's the negative root of negative 1 plus 2. So that's the negative square root of 1. That really is negative 1. So both of these points are where they belong. And we can rest assured that this really is the correct graph. Both of these points are where they belong. Let's do one more. H of x equals 1 over 1/3 of x plus 1 and minus 3 on the outside. So some of these things are transformations, I'm sure. A 1/3 next to the x, that's a transformation. A plus 1, well, that's a transformation. A minus 3, that's a transformation. The only thing here that can't be a transformation is x being in the denominator. So our parent function is going to be 1 over x. I'll draw that right here. Just for easy, let's keep track of the points. 1, 1, and negative 1, negative 1. Now we need to list our transformations, don't we? If there's a horizontal shift, it has to go first. That's this plus 1 right here. The input is this whole denominator. It's 1 divided by the input, and then this minus 3 happens to the output. Do you see? This is the inside of the function here. It's all the stuff that happens to the x. The outside of the function is everything that happens after I do the division. So, this plus 1 is a horizontal shift. 1 unit to the left. This 1/3, now that's multiplication on the x. So that's going to be a horizontal because it's inside, and a stretch because it's multiplication. But remember, the horizontals are all weird and backwards. So when I multiply by 1/3, instead of shrinking, it stretches times 3. That's like you get everything for 1/3 of the price. If I plug in a 9, the function's going to see a 3. Okay? So that's going to be a stretch times 3. And then this minus 3 on the outside, that's easy. It's subtraction, so it's a shift. It's outside, so it's vertical. And verticals are normal, so that's 3 units down. All right, and we're ready to go. If we shift 1 to the left, the whole graph is going to move over a little bit. So this will, a little more than that. This will be the point 0, 1, and this will be the point -2, -1. I've subtracted 1 from each of those x coordinates. Next, we're going to do a horizontal stretch times 3. So everything's going to get much fatter. 0 times 3 is 0, but -2 times 3 is -6. And we don't change the y coordinates. This is horizontal, so we only change the x coordinates. Finally, everything has to move 3 units down. So 0, 1 moves down to 0, -2. -6, -1 moves down to -6, -4. Having trouble here. Okay, so there's our graph. And you can check your work. If I plug in a 0, I'm going to get 1 divided by 1 minus 3, and that really is -2. If I plug in a -6, this whole thing is a -2. Add 1, and we've got -1. 1 over -1 is -1. Minus 3 is -4. So these points are where they belong. All right. Oh, I know. Next, let's say we have a graph. I'll do a couple of these. Let's say this is the point 3, 1. And let's say this is the point 4, 3. And those are both on a parabola here. And I want to find the equation of this parabola. Well, just looking at the graph and trying to figure out, well, y equals what, ax squared plus bx plus c, that's going to be tough. But if I think of these as graph transformations, the first two I can spot immediately. To get here from the parent function, To get here from the parent function has its vertex at 0, 0. So I must have gone 3 to the right and 1 up. There's one more transformation, and this one's a little tricky. On the stock parabola, the default, I have the points 1, 1 and -1, -1. So if I go 1 to the right, I go 1 up. And if I go 1 to the left of the vertex, I go 1 up. If I go 2 to the right, I'd go 4 up, and so on. But it has this nice pattern of if you go 1 to the left or right from the vertex, you go up by 1. But here, I went 1 to the right, and instead of going up by 1, I went up by 2, from 1 to 3. So on the basic parabola, I go 1 to the right and 1 up. But over here, I went 1 to the right and 2 up. What that indicates to me is that this thing has been stretched vertically. It's twice as tall as it used to be. So I'm going to say my last transformation is a vertical stretch times 2. So let's write the equation. We'll start with y equals x squared. We'll do a horizontal shift 3 to the right. That means the input, and that's this x, gets a 3 subtracted from it before anything else happens. So that's on the inside. Now the verticals are on the outside. I need to do a vertical stretch times 2. So I'll multiply 2 on the outside, and I need to do a vertical shift 1 up. And so I've got my equation. We can check that this works. If I plug in a 3, I do just get a 1. If I plug in a 4, I really do get a 3. So this is the equation for that parabola. By the way, just a funny coincidence, this equation is in perfect square form. So if I handed you just a random quadratic, like how about y equals x squared minus 8x plus 14. I don't know how to graph this right off the top of my head, but I could find out real quick. And the way I'd do that is I'd complete the square. I know there's a perfect square. X squared minus 8x plus what? It's been a bit since we did this, so let's review. This is going to be x minus something, x minus something. Those two somethings have to add up to 8, so they're each going to be 4. 4 times 4 is 16, so this would be the perfect square. So I'm going to rewrite this as y equals x squared minus 8x plus 16 minus 16 plus 14. Or x squared. So these first 3 terms are the x minus 4 squared that I want, and then the last thing is a minus 2. So now I know that this is a shift 4 to the right, and this is a shift 2 down, and those are the only transformations. So y equals x squared minus 8x plus 14. The vertex is going to be right here at 4 comma negative 2, and then the parabola is going to look like normal from there. So this is the graph of that function. Easy as that. I think that's a pretty useful technique. All right, so that is graph transformations. And that's all for chapter 3 for this unit. We'll see 3.7 in unit 4, because that has more to do with unit 4 than it does with unit 3. Other than that, for the rest of this unit, we're going to be exploring chapter 5, which is all about polynomials. We're going to get very, very familiar with polynomials in the next bit. All right, see you then.